Faustina Kravietz, and together with this amazing group of collaborators, we wrote this paper, which we hope explains automatic differentiation in relatively simple terms, and it describes how to get an asymptotically efficient reverse mode AD translation for a purely functional language of higher order functions, which is still simple enough to be proved correct. So very quick reminder, what is differentiation? Well, if I have a function f, and it's a differentiable function with n real numbered inputs and a single real numbered output, its derivative f prime, it's f's best linear approximation at some point in the input space. And the lollip here means linear in the algebra sense, not in the programming language sense. So this is a linear mapping, so a mapping that's additive and it scales nicely. That's all it means. And you might notice that there are these little deltas that I use. I'll use them throughout the presentation to signify that a value should be thought of as living in this linear approximation world or this derivative world. Some people like thinking of these little deltas as changes or little changes, which can be misleading in reverse mode AD, but it might be a sufficient intuition for the sake of this presentation. So a delta R is really just a real number, and the same with a delta of a real numbered vector. Delta is just a hint that is kind of to be thought of as a derivative. Okay, so what are partial derivatives? Well, we have the same function. It has n partial derivatives. And you can think of each of these partial derivatives as kind of a one-dimensional projection of the full derivative f prime from this previous slide. And if we want to get the partial derivative out of this f prime, what do? Well, we pass f prime a point. It's this x is the point in the input space. It's bold because it's a vector. And we pass this one hot vector as the second argument, which says that we want the derivative with respect to this one input and nothing else. Okay, so that's enough math. And what do we computer people think about differentiation? And we think that it has to be automatic. So what is f now? It's the same, but it's a computer program. So it can be implemented in terms of pairs and lets and ifs. In fact, if you read our paper, you'll see that we talk about AD on functions that have a more general type, S to T, not necessarily R to the N to R. But in this talk, I'll just talk about functions of this type because it's simpler. So we want to know how to compute derivatives automatically and how to compute partial derivatives, and most importantly, how to compute the gradients. So all the partial derivatives at the same time. So the simplest way of doing AD is forward mode AD. What we want is a source-to-source translation, and we'll call it big F, like forward. And it will take the AST of our original program F, and it will produce a new program which has a very similar type to what we want. The only difference is that along with the derivative, we return the original value that F would return. This is because when we're doing a compositional translation, everything becomes just a little bit easier if you package the program up with its derivative, because sometimes you might need this primal value to compute the derivative. Also, I got rid of the lolly here for simplification, but this is still a linear mapping. It's just that this is the original result of F if we applied it to the input. You might notice that if you kind of ignore the currying, we have two vectors of the same length here, and we can repackage them into a single vector of pairs of real numbers instead. And when we do that, we arrive at what we call the dual numbers approach to forward mode automatic differentiation. So it's really simple. All we do is we translate all the real numbers, all the occurrences of real numbers in our program with these dual numbers, which are effectively just pairs. So the first element of each dual number is the original value that the real number had in the program. The second value in the pair is the derivative. So if we want to translate a function r to the n to r, well, the translated function will have a similar type, but instead of the reals, we'll have these dual numbers, these pairs. And if we want to have a partial derivative with respect to the ith input, we will give a bunch of dual numbers which have zeros as the second element, and only one of them to indicate that this is the variable with respect to which we want the partial derivative to be calculated. So that's so far super simple. And obviously, if you swap out all the real numbers in your program for dual numbers, you will also need to overload all the implementations of the real numbers primitives. So for instance, for addition, well, the first element of the resulting dual number of the dual number equivalent of addition will be normal addition as promised, nothing changes. And here we'll use the calculus rule, or the rule that calculates, dictates, is, well, the derivative of this operation. So for instance, in the multiplication, we'll have the result of multiplying P and Q, and we'll have the product rule from Wikipedia or our calculus graphs, very easy. So this is super simple still. If you wanted to have more real number primitives in your language, you could. For instance, if you wanted to have sign, which is not necessarily implemented in terms of multiplication and addition, that's fine. You just have to give its dual number implementation. But we won't really be interested in that in this talk. Okay, simple example. Let's have a function f, a program f. This is its implementation. It takes two real numbers, returns one real number. This is the translation that our source-to-source transformation will produce. The type of the result, like the type of the resulting program, is the same shape, just with the reals substituted with dual numbers. And even the implementation looks almost exactly the same. Just the sign has been replaced with, well, the dual number version of sign, and the multiplication has been replaced with a dual number version of multiplication. That's it. And if we want to invoke this translated program to get, for instance, partial derivatives, we just need to pass the appropriate dual numbers. So if we want a partial derivative with respect to x, we give a dual number which has 1 paired with x and 0 paired with y. If we want the partial derivative with respect to y, we pair 1 with y and 0 with all the remaining variables, so x in this case. So we can get singular partial derivatives pretty easily from this forward mode translation on dual numbers. And we can present this source-to-source translation in this format, and it looks like a lot of text, but it's actually really simple, especially if you look at the stuff on the white background. That's nearly homomorphic, like pairs go to pairs, function applications go to function applications. Nothing really happens. All the work that happens in this source-to-source translation, all that's really meaningful, happens on real numbers. So if we have a constant of type real, then we will translate it to a constant, which is a dual number. And this dual number will have, well, the original number of the value of the constant, and it will be paired with a 0 because constants, the derivatives of constants are always 0. And if you have, for instance, addition of real numbers, we'll have to substitute it with, well, the addition on dual numbers that we saw a few slides ago. Same with all other primitives on reals we might have in a language. And that's all we do to get a dual numbers translation of a program. That's it. Very simple. So what are these reverse derivatives that everybody's interested in? Well, this is the type for type of our reverse of our dual number translation. But you might remember that before we repackaged stuff into these pairs, into these dual numbers, we had this original definition where we said, okay, we'll want to have a program which takes a point in the input space of the function, takes a direction of change in this input space, and tells us what direction the output will change if we are given this change to the input. So reverse mode AD wants kind of the opposite thing. It says, well, give me a point at which we're differentiating in the input space of the function f, and give me a desired change in the desired direction in the output space, and I'll tell you what the direction of steepest change is in the input space that corresponds to this desired direction in the output space. So this is, in fact, this direction of steepest change is the gradient, so the vector of partial derivatives. And as we saw, we can get the partial derivatives from forward mode by passing the appropriate dual numbers. It's really easy. And then we can package up the results of running forward mode once for every input, and voila, we have the gradient. So what's the problem? Well, the problem is that most people who use reverse mode AD deal with applications which have huge input spaces. So we have functions with millions of inputs and one output, for instance, like in machine learning, where engineers will pump data through their huge networks with millions of parameters, and then they'll estimate something. They will compare these estimates to some sort of ground truths, and they'll produce a number which defines how good these parameters are. And they'll learn, this network will learn by gradient descent, so by calculating the gradient of this loss, so how good these variables are with respect to the weights themselves. So this function has millions of inputs and one output. We can't really get the gradient by running forward mode millions of times. That just isn't feasible. Well, obviously there are many engineering solutions to this. They're astonishing implementations worked on by huge teams, and they're amazing pieces of software. And the problem is that they're huge and complex and really infeasible to prove correct. And we also have really amazing papers with sophisticated proof techniques about AD, but they very rarely focus on efficiency. So what we would like is something that gets a bit of both worlds. So we want an reverse mode AD translation that is asymptotically fast, but still simple enough to be proved correct. And we will achieve this by starting from this simple forward mode translation on dual numbers and applying a few incremental optimizations, and we'll arrive at something that calculates gradients quite efficiently. Okay, so this is the reminder. We can get, well, a reverse derivative or a gradient by running forward mode once for each partial derivative we want. Pretty easy. And one thing to notice here is that there's a lot of repeated work. Every time we invoke this translated function f, we follow the same control flow because we are differentiating at the same point f, at the same point x, sorry. So this could all be optimized, and we could just run all of these invocations of forward mode in parallel. And that's what we can do in our first optimization. So instead of using dual numbers, so these pairs of numbers, we can use multi-dual numbers. So these pairs where each real number now will carry around an entire vector of derivatives rather than only one derivative like it did in the dual number approach. So this vector of derivatives will be all the derivatives from all the runs of forward mode that we'd have to do one by one. And this is pretty simple. The translated program has expected type, which is analogous to the dual numbers type. But now we have this multi-dual number of the entire vector. And indeed, we can get the gradient with only one invocation of this new translation. We call it R, like reverse of f. All we need to do is, like in the dual numbers approach, if we want to differentiate at a point x, we have to distribute this vector x over the first elements of all these dual number pairs. And for each dual number input, or this multi-dual number input, we'll have to give a one-hot vector, which specifies, well, the appropriate derivatives. So for instance, the first input, we will have 1, 0, 0. And then for the second input, we'll have 0, 1, 0, 0, 0. Again, very simple. And the source-to-source translation is very, very easy and simple, similar to the dual numbers translation. All that really changes is that instead of single real numbered values, we have now vectors. So the translation for a constant of the type real will be, well, again, that constant again, paired with a vector of zeros. And if we have addition, we'll have now element-wise addition of vectors. Pretty simple. That's pretty cool. We only have to run the translated program once now. And the size of the source code of this translated program is comparable to the size of the original program, which is good. We don't have any crazy source code explosion. But we do have ridiculous memory usage. If we have a vector of if we have a function of 1 million inputs like machine learning people do, and each of them carries around another vector of 1 million elements, well, that's pretty bad. And also these operations of vectors, they do a lot of work, and they do a lot of unnecessary work because there are lots of additions of zeros here. So the natural solution is to have a symbolic vector representation instead. So this is almost the same as the previous version. The only thing that changes is instead of having vectors that are represented explicitly as arrays of values, we will have this delta structure, which has 4 constructors, and they're enough to represent any vector of reals because, well, you can imagine we can add up a bunch of scaled one-hot vectors and get, any vector of reals we would really want. So these will be our new dual numbers, original value and symbolic version of this vector that we had in the previous version. The source-to-source translation looks similar again. If we have constants, we will now have a 0 vector as the second element of our dual number, but this will be a symbolic 0 vector, which is an improvement. And if we have addition, well, the result of adding 2 derivatives will be the symbolic vector represented by the addition of these 2 symbolic vectors. So this looks good, but there's one problem. And that problem is, if we evaluate this program, we will get this symbolic multi-dual number, which has a real number element, and then it has this tree, this weird symbolic vector, and we might want to have an explicit representation of this vector at the very end of our program execution. So we can do this naively and execute this structure using like this very simple intuitive evaluator, this would work. But the problem is that it brings back a lot of the inefficiencies of the previous version. So long story short, we have a slightly better evaluator, which is faster and also works in place. There's no time to look at it in detail, but it works fast. And another advantage of these deltas is that they're very good for sparse vectors, because the fewer non-zero elements you have, the smaller your tree will be, or your delta tree will be. So this version is really cool because it seems like, again, the size of the transformed program is what we want it to be. The operations on symbolic vectors are cheap. We have in place evaluation of this symbolic delta structure. It's all great, but we have one issue, and that issue is loss of sharing. So imagine we have a very simple program F, which adds its argument to itself, and this is translation. So far, so good. And we have a program G, which applies F 3 times. And this is its translation, also simple and homomorphic, looks fine. But let's try to evaluate it. So 1 gets added to 1, we get 2. D gets added to D, well, we get a symbolic vector as DD, looks good. We did it, do it again, 2 gets added to 2 is 4. But wait a second, like we had two delta trees here, which are identical. And instead of somehow collapsing them, instead of preserving knowledge about both of these subtrees being identical, we're building this possibly exponential delta tree, which we'll only be able to evaluate later once the first pass of evaluation is done. So this will indeed explode. And this is bad. It's almost reminiscent of symbolic differentiation. So what we need to do is preserve this sharing somehow, and we'll do it using memoization. So we want to ensure that all the trees that come from the same source, so the identical trees, are evaluated only once. And because a tree with sharing is just a DAG, we can represent a DAG as an expression of let bindings. So we can take our original delta and expand this data structure of 2 new constructors, which are called var and let. And these will express the sharing. And because we need like pure functional languages and they're easier to prove correctness of, we will keep information about the state in a monad. So the translation is now a little bit more complex, including for the cases that used to be homomorphic, but it still doesn't really do that much. So these are what used to be the boring cases. They're still the boring cases. But if you look closely, it looks quite complicated, but this is just a standard monadic translation for a call by value. What the really interesting stuff happens, again, at the real numbers types. And the difference is that instead of creating one huge tree, every time when we, for instance, add two trees, we give that new tree a name. So effectively, we never create one huge tree. We create these tiny trees, tiny delta structures, and they point at each other with these let bindings. And then we preserve information about sharing. Well, if you're familiar with other reverse mode AD approaches, like the state of this monad can be a little bit reminiscent of like a tape or a Venn grid list. And if you look at our evaluator, which we also don't have time to look at in detail, the interesting thing is that we also have these 2 passes. First, we evaluate the program, then we evaluate this delta. But during the evaluation of this delta, we do things backwards. We first evaluate the body of the let, so U2, and then evaluate U1. So this is a little bit similar to a forward and reverse pass in other reverse mode AD approaches. We have more detailed implementation sketches in our paper. Okay, so this last translation, the monadic translation, it's asymptotically efficient, both in runtime and in space, and both passes, so both the evaluation of the program and the evaluation of the symbolic delta, both of them are asymptotically efficient. That's important because that's the problem that the previous version had. The program seemed to be asymptotically efficient, but the delta structure evaluation was problematic. We have a proof of correctness. Well, there has been much earlier work on correctness of AD, especially forward mode AD. But because we have this sharing, we had to use a cryptological relation and to capture kind of the growing environment in our state monad. I don't think we have much time, so let's just sum up that the final monadic translation basically does everything we want it to do. It's fast and it's provably correct. And it does support higher order functions really trivially, as we saw. We didn't really think about them in any explicit way. And we didn't really talk about this, but it's interesting that thanks to the translation being compositional, we can support separate compilation. So if you, for instance, have a library function, you don't really have to retranslate this function every time you use it in a new program and you translate that program. You can do it separately. This translation also works on a more general type S2T, as I mentioned, and we can easily extend our language with more primitive operations on reals and by arrays. So in conclusion, we kind of started with very simple forward mode on dual numbers, and it turned out it wasn't that hard to get something that may or may not be reverse mode, but does calculate derivatives, or calculates gradients, so all the partial derivatives at once, and does it asymptotically efficiently. And we have a proof of correctness, and many of the techniques in our paper are actually not very new, but the combination is, which we find quite interesting. And we also hope that the exposition in our paper is well simple enough that even newcomers to AD could understand it and build on it. Well, thank you. I think that's all.
Thanks for the talk. So I'll take any questions you have, and if you're online, a reminder to post questions in the Q&A tab instead of the chat tab. 1 second.
Hi, thanks. Very interesting talk. So
I can see myself a million times now.
Hey, so interesting talk. So I'm also quite interested in this problem. Reverse mode. So I was kind of curious what kind of efficiency gains one can actually get, like, in practice for, these types of problems. You'd mentioned things like memory consumption of forward mode. And so I was curious, like, empirically, for your guys' work, what kind of gains one can expect for like, these types of benchmarks that, people care about. So, yes.
So our work specifically, we haven't really done like a usable implementation yet, like the implementation for the working machine learning engineer. But well, I think the important takeaway, which I guess most people understand, is that usually it's infeasible to run forward mode many times. People use this reverse mode, and we can't, I think, really compare ourselves to something like TensorFlow or PyTorch at all. But other reverse mode techniques we have seen for higher order functions in functional languages, they aren't really even asymptotically efficient. So there, okay. Actually, I'm sorry. There's a interesting anecdotal exception to this. There's an AD library in Haskell which we discovered actually post factum. Does many things very similarly to us, and we're actually right now comparing kind of our implementation against theirs, and it seems comparable. The difference is that there's this Ed Kmetz library, and I think it's based on Perlmutter and Siskin's work, and he does things, I think, statefully mostly. I'm not sure about this. And we think that we're basically as efficient as they are, but we can prove correctness while they can't. So I think the gains are not as good as TensorFlow PyTorch, but they're very good for functional programming languages. I don't know. Well, I can't see or hear anybody anymore.
Oh, sorry. Got one other question. I appreciate the earlier illustration of how higher order your method was.
Sorry?
So thank you. This is okay. So I'm still trying to wrap my head around this. This seems cool. I've implemented forward and reverse mode, and it was really painful to implement reverse mode, and I had to stop being functional in the past. So I'm really excited about the possibility of doing this right. What you described sounded like you were doing forward mode evaluation, but with a much more efficient representation of the gradients that would then give you the efficiency of reverse mode. I guess I think reverse mode is something where you're computing at each point in the evaluation the derivative of the with respect to the final output of the right. You're comparing the particular node in the AST, say, with the final output. But it seemed like you were still doing something that was more like forward mode, but with the nice properties of reverse mode. Is that fair?
I think that's a very good summary. I was wondering whether this would be confusing. We put reverse mode in the title of our paper, and looking back on it, we said reverse mode because the point of reverse mode at the end of the day is to calculate a gradient, and that's what we do. But it's fair to say that I don't think that this is what many people understand reverse mode to be. People have a pretty, I think, there's no good definition of what reverse mode versus forward mode is. There's like one book. So many people think reverse mode is a specific thing which uses a tape and uses this forward and reverse pass in a very specific way. So maybe you're right that what we do is actually forward mode, or it should have a different name. But the takeaway is that yes, we do the entire gradient or many runs of forward mode, but it might not be reverse mode automatic differentiation.
In the end, you're just using the chain rule, and I guess the question is, which direction does the chain rule run?
Yes.
But this is cool. Thank you.
Thank you.
Okay. I think that we need to get moving to the next talk. Thank you very